really a good question. It's kind of a high-level question here. And I would actually have to look it up. I think usually the rearranged product becomes the major one because it comes from a tertiary carbocation. And the thing about these rearrangements, they're actually spontaneous. They happen instantaneously. It happens even faster than water attacking. And the reason it happens faster, if we think back to yesterday's lecture, is it better for a molecule, faster for a molecule to move electrons around within itself or to find another molecule out there floating around in a flask. So usually intramolecular processes are faster. It's not going to be universally true that this is the major product and this is the minor product. It'll be very, very substrate dependent. And notice that I'm not putting in yields here. I'm not saying this is that, this is that. Notice I'm not saying this is major, this is minor. So you can see already that that's not the emphasis here. It's not a question I'm interested in. Students will struggle enough to explain this. And that's what I'm more interested in is, you see a reaction like this with something unexpected. Can you explain it logically using mechanistic errors? Yep, so here's another question about it for this beta step where we're redrawing things. I'm not going to answer this question directly whether you have to draw out every possibility, right? The question here is, can we just go to the one we know is going to give rise to explaining this, right? Maybe some of you will work very quickly, as I alluded to, that you'll turn all your attention to the beta 2 position. Well, when I ask you to explain this, you have to make sure you do the work necessary to explain this. I think examining both positions means you'll never make any mistakes, you'll never miss one. But if you can really explain this particular process, then drawing both is not necessary. I think when practicing, though, drawing beta 1, beta 2 doesn't take that much time. Doesn't take that much time to draw these two things, and even on my exams, which are 4 pages long, you have 75 minutes for them. You have a lot of time to sit here and think and ponder these types of issues. So maybe you don't have to draw all of it, but if your goal is to explain this product, right, then you definitely have to pick the right one. And if you miss this, just casually go to the wrong one, it's over for you. You won't be able to explain this, okay? Absolutely need to know the mechanism of carbocation rearrangement. Yeah, I'm taught it to you. You have to be able to demonstrate this, have to be able to identify when an energetically favorable process happens or when an unfavorable process happens. You better reject it, just forget about it. If you keep working with this, it's wasting time. So this process is very slow, very methodical. Your questions, I totally get it, but you do need to know this mechanism. But if you think about all the lectures we're going to have 7 lectures for our 3rd exam. This little portion we're talking about now is about 30 minutes of those 7 lectures or 14 hours of material. So please categorize it by how much time we've spent on it. It would be ridiculous to think that 90% of the points on the exam will be from carbocation rearrangements in the big scheme of things. So again, if this is very challenging for you and you're feeling a little bit concerned about other portions of the material, please, you have my absolute blessing and absolution that you should study those other things, all right? But once you've made it through those to reach the very highest level of understanding in this course, this is part of that curriculum. Let's put a few more examples here. We have about another 5-10 minutes, so I just want to put up a few more examples. If we have time, I'll work through them, but maybe I'll just put them up as on your own examples and just give you some clues about how we would address them. This will give you some best possible practice for these. Let's take another SN1 reaction. That's where we're working with today. And SN1 reactions involve carbocations. We're going to take this secondary substrate, okay? And I'm going to leave out stereochemistry. These aren't dashes or wedges. This would matter for a stereochemical question, which this one is not. If we take methanol and heat here, this is a particular problem. Secondary substrate, heat, methanol. Could go either way for SN2 or SN1. Leaving group's great. Solvent's bad. Not a good nucleophile. And we see a mixture of products. All these things tell us that we have a carbocation reaction or a SN1 reaction. Bad solvent, weak nucleophile. We have products where we have skeleton rearrangement. The alcohol or the ether that we're making definitely forms right where we would expect it. Then it's in an unexpected place. There's been some sort of skeletal rearrangement. This particular problem, I could say to you, give a detailed step-by-step reaction mechanism that explains the formation of these two major products. This one, very, very, very straightforward. This one involves carbocation rearrangement. So even in a problem like this, if it shows up on the exam, if you can just do this much of it, that's a significant amount of the point of the problem or the purpose of the problem. Students who get to B and A level of mastery would be able to take it that step farther. Okay, one step farther for this. So this is kind of an on your own type problem. One thing I'll do, I'll just give a little bit of a clue here for this. We have a little bit of time. Let's just do the first step together. You have to say it's SN1 right away. Can't ignore that. Means we have to draw carbocation right away. Okay, this is our secondary carbocation. To get to the secondary product is easy. Add methanol to this. You would have to draw that out in a long series of steps. You know how to do it. Work that out on your own. But I want to talk about this particular carbocation. Let me just redraw it. A little bit more fidelity here. This is our carbocation. This is our alpha carbon. We have two beta positions. Are they identical or are they different? These are different. So we're just going to label them beta 1 and beta 2. It's arbitrary that I'm calling them beta 1 and beta 2. Call them blue. Call them green. Call them, don't use little Roman numerals, use capital, like Western numerals here. It doesn't really matter. I'm doing this on purpose so that I don't forget anything. I'll leave some little clue here for you to explore. At beta 1 position, we have hydride to consider. This beta 1 position, we have hydrides. We could move them. Where would the carbocation be? Would it help us explain this one? At beta 2, we have hydride to consider, and we have a methyl group to consider. At the beta 2 position, we have two sources of electrons. We have this hydride bond, and we have this methyl bond. In the last example on the last page we were working on, we moved a methyl group. We could also move a hydride here. So here, there's actually three choices of things that we could move. Okay, there's three choices of things we could move. We have those two hydrides. We have this hydride. And we have this methyl group. And the way we would move them, one at a time, we would draw beta 1 position, move the hydride, draw the carbocation. So we're starting from secondary. What happens if we move a hydride? What type of carbocation do we go to? At the beta 2 position, if we move the hydride, we have a secondary carbocation. What does it go to? At the beta 2 position, we could move the methyl group, like we did in our last example. What type of carbocation do we make? In any of these, do we make a more stable carbocation? In any of these, do we work towards a carbocation that resembles something that would allow us to explain this particular rearranged product? That's how you think about these things. So lots of clues here. There's a little bit more to consider than in our last example. We have two beta positions. One of them has hydrides. The other one has a hydride or a methyl group. Just practice this. I think you'll really get to this easily. You'll understand perfectly what has to happen here in this particular example. I'll put up one other example that's similar to this for you to practice as well. But here I've given so many friggin' clues, but you just have to do the work. The work's up to you. answer these. And if you can answer this, you can answer this. Some of you are looking at this right away, already know what to do. Some of you are looking at this and you're thinking, I don't know what to do. Go back in the notes, practice what we did on the last page carefully, then apply it to here. Okay? And then finally, last one. Here's one last one. Let's take water and heat for this particular substrate, and I could simply say, give a detailed reaction mechanism that explains the formation of this product. Okay? Give a detailed reaction mechanism that explains the formation of this product. If you draw SN2 reaction mechanism here to start, it's over for you. It's minus 8,000 points. This is secondary substrate. It's very bulky. Water is not a nucleophile. Water is a bad solvent. This is rearranged somehow. There's no reason to think that you should draw arrow, arrow. You should draw arrow departing, carbocation forming, explaining somehow how the carbocation moved from here to here, then water goes in. So again, this is how these types of rearrangement products will be set up for you. I won't ask you to anticipate a rearrangement, but I will ask you, just like we practice in class, explain a rearrangement, explain this unexpected phenomenon, and you do this through the process of arrow pushing and using a right mechanism. And again, carbocation tells us, or a rearrangement tells us, we have to have a carbocation. So if you just start with a SN2 mechanism here, it won't go well for you. So again, this is why I'm saying over and over again, make sure you understand SN2, make sure you understand SN1, then and only then try these more advanced problems. Again, some of you, I'm sure, get this right away. That's fine. Some of you don't get this right now. That's fine. All these scenarios are absolutely okay, but this is where you need to work towards. And once you get here, then everything that came before it, you've mastered and will do great on. And if you don't get here all the way to the end in time for our exam, there's still lots of other places where you can have great success. So this really wraps up what